Hi everyone, in this video I'm going to do the solutions to the 3 chain rule examples in the notes. So all 3 of these are going to use the chain rule, so we'll remind ourselves what that is before we continue. So the chain rule is a rule for computing the derivative of the composition of functions that you have derivative rules for, right? So e to the x we have a rule for, x to any power we have the power rule for, but then when you combine those things, similar to what we have here, you need to use the chain rule to kind of glue their individual derivative rules together. So the derivative of a composition f of g, so I'm going to put this in shorthand. This is a little bit different than what it looked like at the beginning of the section, but it means the same thing. So I have a function g plugged into a function f, and I'm going to say the derivative of that. So I have this prime symbol here. So your derivative would be f prime of g. So that's g, the original function g, plugged into this guy's derivative. And then you multiply that times g prime. So it's the derivative of just that inside piece. So for each of these 3 examples, I want to decide what would the f and g be, compute their derivatives separately, and then plug into this formula every time. Alright, so let's start with number 1, which is 5x squared plus 3 raised to the 4th power. So I'm going to decide that my f is supposed to be the outside function, right? So I'm going to say that f is the 4th power because that's kind of the outside operation that's happening. So my f will be x to the 4th, and then my g will be the stuff inside the parentheses. Now, the more practice you get with the chain rule, the easier it's going to start to get to pick your f and g. But for now, you want to just kind of try something, right? And if you're not 100% confident in what you've picked for f and g, take a minute on the side and compute f of g of x, and make sure that it really is the function that you started with. Okay, so I've picked my f and g. I know that they work, so f of g is this function here. So now I want to compute f prime and g prime. So the key here is that you want to pick f and g to be functions whose derivatives you have a rule for. Right, so these weren't the only f and g you could have picked to compose to this, but we've kind of separated them just so that each of these we could do derivative rules for. So if you end up in this spot and you don't have a rule for it, you may have a little bit more work to do. Okay, so if f is x to the 4th, f prime, I will use the power rule and get 4x to the 3rd. Your power rule is nx to the n minus 1. And then the derivative of 5x squared plus 3 will be 10x, that comes from the 2 times 5x to the 1, and then plus 0 because of that 3, so I'll just leave it as 10x. Okay, so now I have all 4 pieces, so I'm just going to plug what I have into the chain rule here, and that'll be my final answer. Alright, so my derivative h prime of x, I want f prime, so that's 4 times something cubed. But I'm going to plug the original g into it. So I'm going to take this function and plug it in here. So I have 4 times 5x squared plus 3 cubed. So that's my f prime of g. I should actually label this, at least for the first one. So this is f prime of g, using this f prime and this g. And then I'll multiply this times g prime. So for us, g prime is 10x, so I'm just going to write times 10x, and that'll be it. In future problems, what you may have is that g prime is multiple terms, right? So it's like 10x, like plus a number or minus a number. That means that in this step, you would have to have another set of parentheses around the g prime. Anytime there's addition or subtraction there, you want to make sure it's clear. But if it's just one term like this, the parentheses are not entirely necessary. All right, so we'll continue labeling here. That's my g prime. For most of these, the instructions will say don't bother simplifying, so you can just kind of leave it in this form. If you did want to simplify this, you would definitely not multiply this out because that would be unhelpful. But what you could do is say, oh, 4 times 10 is 40, so maybe 40x times this stuff cubed. So I'll leave that as my final answer and move on to problem 2. Alright, so I have a very similar setup here for this function. Notice that I've named each of these functions h of x, which is a little bit unusual, right? We usually see f or g. The reason I'm doing it for these examples is just so that we don't get any interference with what f and g are. In future problems, if your function is f of x, you just want to remember that when you do this formula, this f and this g are completely different from that f. Okay, so again, I want to start by deciding what f and g would be. So we want to pick these functions so that f of g of x is this function here. And we want to make sure that they are two functions whose derivatives we have the tools to compute. So I would choose that f is the square root of x, because that square root is kind of my outside operation. And that would make g the polynomial inside, so x squared minus 5x plus 2. And again, if you kind of take a little bit of a leap in this step and you're not sure, pause at this point, compute f of g of x off to the side, and just double check that it gets you where you want it to be. And if it doesn't, kind of tinker with it and try again. All right, these work, so I'm going to do f prime and g prime. The square root of x, you may have that derivative rule memorized already. It's one that comes up a lot. If you don't have it memorized, that's totally fine. You just want to remember that the square root is the 1/2 exponent. So this and this are the same thing, just written in different ways. And when you write it as x to the 1/2, you realize you can use the power rule, just like we did with the 4 in the first example. So its derivative will be 1/2 x to the negative 1/2. This is negative 1/2 because that is 1/2 minus 1. You may also write this as 1 over 2 square roots of x. This is like the pretty version of the same thing, but either one of these will be okay for us in class. I'm actually going to use the one in blue, just to keep things simple. Okay, so g prime will be 2x to the 1 minus 5 plus 0. So that's 2x minus 5. Just using the power rule for both of them. Okay, so now I have all 4 pieces, so once again, I'm going to go back to my chain rule and plug things in. So I want f prime of g times g prime. Okay, so my derivative will be f prime with g plugged into it. So I'm going to put this polynomial in here. Times g prime. So this is an occasion where g prime is 2 terms because you have that subtraction. So we definitely need that set of parentheses right here. Without these parentheses, the 2x would be multiplying by this, and then minus 5 would be on everything, whereas you want to actually multiply it all together. So extra set of parentheses there, and that's my final answer. All right, we've got one more to go. So my third example here is the sine of 5e to the x plus x. All right, so again, I want to start by coming up with f and g. I'm going to say f is sine of x. This is one of those functions that looks like multiplication, but it's not. This is being input to the sine function. And then g is 5e to the x plus x. So when I plug this into the sine function, I get my original function. All right, so we have a derivative rule for sine of x, so that would be cosine of x. And remember, the derivative of cosine is negative sine. G prime 5e to the x is 5 times the derivative of e to the x, so it's still just 5e to the x. And then plus the derivative of x, which is 1. All right, so one more time, I'll use my chain rule. I want f prime of g times g prime. So h prime of x equals, all right, so f prime is cosine, and I want to plug g into it, so I'm going to take this function and plug it in, times g prime. So I'm going to multiply by this, and just like the last example, it'll have a set of parentheses around it, so I have 5e to the x plus 1. So what I have is the cosine of this stuff, then times 5e to the x plus 1. And that is my final answer.